Strange behavior in certain animals, particularly dogs, cats, horses, and others, can be seen just a few minutes or hours before a volcanic eruption. Many people believe that Earth's movements in some way stimulate the dog's turmoil. Why does this happen? A theory suggests that wild and domestic animals are able to feel the vibrations of Earth before humans do. Another theory is that certain animals, such as dogs, are able to detect electrical changes in the air emitted from Earth. Whether these theories are true or not, people and nations around the world still rely on the instincts of animals to save them from natural disasters. But could this behavior possibly help us as humans predict volcanic activity? The world is a ticking time bomb, and scientists are racing to find answers before it's too late.
Oh, hi! What tools do volcanologists use to predict eruptions, you might ask? Well, there's many different ones. The first and most important is the tool of observation. You can use just about any of your senses to tell if a volcano might erupt. For example, if the ground shakes, that could be a sign. If you see smoke or ash, even magma, I guess at that point it'd be lava, coming out of the top, that's a definite indication of an impending eruption. Many other tools can be useful besides observation, however, in predicting an eruption. One such tool could be a tilt meter, a thermal imaging device, a gas monitor, a seismic monitor, or radar mapping. A tilt meter detects subtle changes in the slope of a volcano. It's an extremely sensitive device. It's so sensitive that it could detect a 1 millimeter incline in a half-mile long piece of wood at a slope, just to give you an idea. So that's extremely sensitive. Using this, you can make inferences about the magma plume within the volcano by detecting how much the slope has changed. If it's increased and become more vertical, there's a good chance that the magma plume within has grown and that there might be an eruption coming soon. The workhorse of all volcanic monitoring is seismic monitors. These record earthquakes as they happen in real time, which allows us to pinpoint the epicenter and the intensity of the earthquake. These monitor all the small tremors that naturally happen around a volcano, and they can pick up when these tremors become more violent or more frequent, which often happens before an eruption. Another good tool volcanologists often use is thermal imaging. Thermal imaging basically works by taking a snapshot of heat. We use these either in stationary cameras that take single frame pictures over a long period of time. They can be high definition video cameras also, attached to airplanes or satellites. Another interesting tool that volcanologists often use is thermal imaging. Thermal imaging is basically a snapshot of heat, or heat signatures. They use these heat signatures to see where heat's coming from within the volcano. These thermal imaging devices can either be a stationary single-shot frame that's either left on the mountain for periods, or it could be one that a volcanologist carries around in his hand, or it could even be an HD video camera attached to a satellite or an airplane. And these are used to provide heat maps. And what they can do with these is they can tell if the heat's increasing or decreasing or moving to a new area. So they're pretty useful in detecting new volcanic activity. Two of the most frequently used methods of monitoring gas are Japanese boxes and spectrometers. Japanese boxes are basically crates that are filled with beakers that contain potassium hydroxide. And as gas leaves the crater, it enters that crate sitting on top, and it reacts with the potassium hydroxide, which will change the solution over time. So what a geologist could do is see how that solution's changed to know what elements were there to change it. Another important one is the spectrometer, which identifies what type of gas is coming from a vent or crater by analyzing the light signatures produced by the gases. Each individual gas will produce its own light signature, so it's pretty easy to monitor which gas is coming out. And in the event of a near eruption, it can allow people to evacuate the people in time to save lives. And that's good.
Scientists have long recognized that gas emission was the leading force, the driving forces in volcanic eruptions. Magma is able to hold gases because of the increased pressure at lower depths of the earth, thus increasing the gas solubility in the magma. As the magma chamber pushes upwards, the bedrock layer gets thinner and thinner, thus allowing the gases to emit from all the magma because of the pressure decrease. When the magma cools, the gas is being emitted as well. Other than free oxygen, which is generated by photosynthesis, all atmospheric gases occurred from the earth. Thus, all atmospheric gases came from a volcanic eruption. The gases can escape to the Earth's atmosphere through fumaroles, active vents, and porous ground. There are three main gases in a volcano: H2O, CO2, and SO2. These gases can be actively monitored in order to keep track of the volcanic activity. Well, there's three main methods in monitoring volcanic gases. The first is measuring gas emission rates and gas plumes. By measuring changes in emission rates, scientists can infer changes of magma or magmatic activity down below. Increased gas emission rates indicate increased levels of activity. Thus, increase in SO2 and CO2 concentrations emitted from fumaroles may indicate magmatic activity down below. For example, Mount Pinatubo in 1991, 1 month before the eruption, there was a huge increase in SO2 emission rates. 2 weeks later, SO2 emission rates were 10 times higher. Right before the eruption, SO2 emission rates decreased intensively. The second method in measuring gas rates in volcanoes is direct gas sampling, in which scientists go down and gather a direct sample of gas, which then they send back to a lab to be analyzed. This method gives explicit composition of the gas, but no emission rate. Gas sampling can be taken from atmosphere, soil, and water. The last and final method, the third method, in monitoring gases in volcanoes is continuous on-site monitoring. Through the use of sensors directly in the vent, records changes in emission rates and sends data directly to an observatory. The composition change and the emission rate of the gas provides additional information on what is going on inside the volcano. People have ever wondered if gas and magma had any kind of correlation. Well, it does. Magma with high gas content correlates to explosive eruption. For example, an increase in the ratio of carbon to sulfur gases can be used to indicate the new arrival of a new batch of magma. When it comes to measuring gases, there are many different ways that it can be done. One way the measurement of gases can be done is through direct measurement, in which gases escaping from fumaroles are collected by scientists through evacuated flasks and analyzed in a geochemical lab. Although much useful data has been acquired through this process, it has been proven to be very dangerous. And there is a great difficulty in collecting samples that are uncontaminated by atmospheric air. Another measurement process that can be used is called the co-spec measurement. It involves remote sensing of gases by a correlation spectrum. The mounting of co-specs on helicopters allows SO2 concentrations to be cataloged on a daily or weekly or whatever basis you need to be done. The distribution and amount of sulfur dioxide released into the stratosphere by volcanic eruptions can be measured by the total ozone mapping spectrum, or the TOMS. Improved TOMS instruments have dramatically improved our detection capabilities, thus allowing us to really use these measurements to help us predict volcanic eruptions. There are many ways we can use monitoring of gas composition and emission rates to predict volcanic eruptions.
Well, satellite imagery has become the newest way to look at the Earth in many different ways. As far as predicting volcanoes go, this new technology that volcanists are able to use lets them see the inflation of the volcano as the magma is coming up to give the appearance of a possible eruption. This machine is known as the INSAR machine, which stands for Interferometric Synthetic Aperture Radar. This machine can be used in a variety of ways on going over many different surfaces of the Earth, in even remote areas and from aerial views. It uses electromagnetic radiation with microwave frequencies that prevent cloud cover, making it much easier for the INSAR to accurately see where the heat flow is going and to possibly tell when an eruption might be occurring at a certain point on Earth. Another great piece of technology that geologists use today is the use of heat flux maps. Heat flux is also known as thermal flux, which is the heat energy transferred through any given portion of the Earth's underground surface. Heat flux maps give us a global or specific picture of the distribution of the heat flow. This allows us to track the magma to see where it's going, along with what it could be doing. The heat flux map is then constructed by measuring the temperature difference of a specific area on Earth's surface over a certain period of time. This is called thermal conductivity. An example of an active volcano zone where up-to-date heat flux maps are a vital part of the prediction of the eruption would be the Yellowstone caldera. Water expelled from Yellowstone's hydrothermal systems carry considerable amounts of heat, reflecting the amount of magma below the surface. This magma thus provides an unparalleled number of hot springs and geysers on the Yellowstone Plateau. Yellowstone is also measured using steam gauges, which tally the total temperature of the heat flow that runs through its rivers. All this data will accumulate for a heat flux map, giving geologists the ability to see how the magma is, how much there is, and when it could possibly erupt.
Alright, we can start. Well, you see, volcanoes are somewhat difficult to predict. We're just now really getting the technology to sort of begin to understand how things really work under the Earth's crust. The problem is, it's always easier to see patterns in monitoring data after the eruption already occurs. Now the challenge is to use this sort of data and apply it to what we already know to possibly help prevent future catastrophes. There are many kinds of tools that volcanologists can use to monitor activity underground, but possibly the greatest indicator of volcanic activity is what we can see on the surface. GPS satellites are constantly surveying the landscapes around volcanoes. If you can imagine, sort of like Play-Doh, it can mold and shift on top of all the heat and pressure that's lying under the ground by the magma. Movement can vary from centimeters to mere millimeters over the course of time. The slope of the ground also indicates the amount of building pressure. It's when we see swelling like this in a relatively small area that really raises a red flag and says, hey, this may be some volcanic activity. But of course, sometimes millions of dollars worth of technology just can't beat going to see things on foot for yourself. Some of the more bold volcanologists have studied and measured ground deformation on foot, on location. Simply horrible working conditions. Just recently, a prototype for a fully automated ground deformation monitoring system called a synthetic aperture radar was released. Although it can have limitations like deep vegetation and moisture, it can have accuracy within an inch under perfect conditions. A recent study actually at the University of Miami used the synthetic aperture radar to study active volcanoes in Indonesia. They watched close to 800 satellite images of 79 different volcanoes between 2006 and 2009, and of the 6 that they found to have significant ground deformation, 3 of them erupted shortly thereafter. They also found several trends of magma flow within the region, which is great because of the location of Indonesia. It's always at a high risk level for earthquakes and other natural disasters. Electronic distance measurements, or EDM, also shows a significant movement. While it sounds really scientific, the big idea is we just stake 2 sticks in the ground and we measure the distance between them over a series of time, and you know, the more distance between the sticks as it grows, that's obviously a mounting amount of ground deformation and magma underneath the surface. By monitoring ground deformation, we can potentially save lives, and that's why I'm in this field. It's just an exciting time. The technology is really, really getting close.